So in the beginning, everything was very simple. There were a few assumptions, and the definitions of the assumptions were also more or less straightforward. So nowadays, the situation looks a bit more complicated. So I'm not going to make a judgment if it's a good idea to introduce too many new assumptions, but I was going to ask the question is, how can we keep up with proving assumptions and checking the correctness of the proofs for these assumptions? So what we propose is to have a tool for the automated analysis of assumptions in the generic group model. So you're given an assumption A in some input language in the generic group model, and you have an analyzer, and the analyzer returns either the assumption is valid or the assumption is invalid. And in the first case, we want to also get a bound, an upper bound for the winning probability of the adversary against the assumption. In the second case, we want to have an algebraic attack against the assumption. So just to give a bit of context, so as we all know, cryptographic proofs are usually conditional. That means if a crypto system is breakable, then the proof ensures that the cryptographic assumption that it's based on cannot be hard. So to actually look at the assumptions on their own, so we base the security of a scheme on an assumption, but we want to know if the assumption is also hard. The generic group model was introduced, and here the idea is that a minimal guarantee for the hardness of an assumption is the hardness with respect to generic algorithms. And here generic algorithms means that the algorithm is independent of the concrete representation of the group elements. And this is ensured by giving the adversary black box access to the group operations, either using handles or random representation of the group elements. This was originally proposed for the simple generic group model and later generalized to bilinear groups and to multilinear groups. And there have also been cases where proofs for the hardness of assumptions were invalid in the generic group model, which have led to breaks of the corresponding schemes. So a common way to perform these proofs is to use the so-called master theorem, or it's also called an Über-assumption. And this gives a way to perform proofs in the generic group models in an algebraic way. And this was proposed by Bonnet, Boyer, and Go in 2005. So I'm going to present the version for symmetric bilinear groups here. And I'm going to use this implicit representation of group elements here. So just this notation where the index denotes a group. So the master theorem states that if the adversary is given implicit representations of P1 to PR evaluated at a random point X in the group G, and implicit representations of the polynomials Q1 to QS also evaluated at X in the target group, then it's hard to distinguish f of X from a random element in the target group. And this is exactly the case if the polynomial f is not in the span generated by products of polynomials pi times pj and products and polynomials qj. So this means, this just reflects that the adversary can use the bilinear map to multiply two polynomials here in the exponent, let's say, and he can also use polynomials from the target group, and then he can perform addition, so that's where the span is coming from. And there have also been generalizations of the master theorem, so I just want to focus on this one, which was presented last year at Crypto. And this is the master theorem for matrix assumptions, but it also takes into account multilinear maps. So in this context, we make the following contribution. So first, we develop a generalized master theorem that is more general in terms of the group settings that are supported. So for us, a group setting is just an indexed set of groups, and then an arbitrary set of isomorphisms between the groups, and an arbitrary set of n-linear maps. And we only have the restriction that if you consider this as a graph, it doesn't contain cycles, and this is a condition that ensures that you cannot perform an unbounded number of multiplications, because then the whole method doesn't work. And the problem types we support are computational problems, left-right decisional problems, and interactive problems. And using this master theorem, we then propose methods to automatically analyze the condition, the algebraic condition of the master theorem for different classes of assumptions. And here we use SMT solvers and computer algebra systems. And we have implemented the methods in a tool, and this tool is publicly available. So here you can download the tool and use it using a web interface. So on a high level, our approach is as follows. So we have an assumption A in the generic group model. And then we simplify the generic group model to something that we call the symbolic group model. So it's a step that is also in all the previous proofs. So the symbolic group model is we compute with polynomials in the polynomial ring instead of the individual groups. And this is justified by the Schwarz-Zippel lemma. And then we have a version. Then we have a version of the master theorem that gives us an algebraic condition derived from this assumption. And then for the automation, we use different methods for analyzing this algebraic condition, depending on the concrete shape of the assumption. So first, our version of the generic group model is a straightforward adaptation from the model proposed by Maurer, which uses handles for group elements. So first, the concrete generic group model is specified by giving a group setting, which is, again, an index set of groups, a set of isomorphisms between the groups, and a set of maps, of n-linear maps. And by the adversary inputs, this is these are the initial group elements that the adversary has access to. And these are specified by giving for each group a list of polynomials. Then the experiment proceeds as follows. To initialize, a random point is sampled, and then for all the groups, the lists are initialized with the group elements corresponding to evaluating the polynomial at a random point. And then the adversary has a black box access to these group elements. So this means the usual group operations proceed as follows. So they take handles, and they look up the group elements in the list, compute the result, always append the new group element to the list, and then return this new handle. So the adversary additionally needs an equality oracle that tells him if two handles point to the same group element. And for the winning condition, also equality of group elements is used. Then in the first step, when we go to the symbolic group model, this just means we perform all the computations with polynomials instead of group elements. So here it means we perform addition and the negation in the polynomial ring. Then isomorphisms just mean we copy elements from one list to another. Bilinear map or n-linear map applications corresponds to multiplication of polynomials. And for the initialization, this is just deterministic now because we just store the polynomials in the list instead of sampling a point and then evaluating the polynomials. And the usual proof technique with the Schwarz-Zippel lemma tells us that there is a small bound on the difference between the two models. So then how do we deal with completion? We basically generalize the approach used by the original BPG master theorem to get rid of all the isomorphisms and the maps, and then just have an algebraic criterion that uses a linear algebra. So we do this. We prove that without loss of generality, an adversary has the following form. So in the first step, he performs all possible isomorphism and map queries, but no addition. So this is still a finite set that he gets out of this. And then in the second step, he performs only additions and zero checks for the polynomials in the target group. So this means if we have an assumption, the original assumption here, which is in an arbitrary group setting G, we can get a modified assumption in the generic group where this is just the result of applying step 1, so applying all possible isomorphism and map queries to the original input, and then taking the resulting list in the target group. So this is what this L hat and R hat is computed from this, given the isomorphism maps, is what we call the completion. Then our master theorem looks as follows. So we have a group setting, an adversary, and a left-right input, which are lists of polynomials of the same shape. And then if the linear relations for the completion on the left and for the completion on the right coincide, which means all the equality checks that the adversary can perform give the same result, then we get a bound on the distinguishing advantage between the left and the right. And this bound depends on the size of the list, on the size of the adversary input, the number of queries, excluding the equality queries, which we consider are free, and on a bound on the degree in the completion. And this is just a standard application of the Schwarzschild lemma. So to perform automated analysis, what we have to do is we have to check this side condition for a given group setting and adversary input. And to do this, we differentiate between 3 different types of assumptions. So the first type of assumption is simple. This is something like DDH in a type 2 group or something more complicated. But what we need here is that the adversary input has a fixed size and the group setting is fixed. And then we can just compute the completion because it's all finite, and we can use linear algebra to compare the linear relations on the right and the linear relations on the left. But if this condition is not satisfied, so for example, if we have so now we go to the second type, the parametric assumptions. And here we might have Q-type assumptions, or we might have assumptions where the arity of the n-linear map is variable, for example. And then we can still symbolically compute the completion, but we cannot just use linear algebra computations to check if the linear relations on the left and on the right are the same. So what we use here is that we translate the whole assumption into a system of inequalities over the integers and then use an SMT solver to check the satisfiability. Unfortunately, we prove that the resulting problem is undecidable, so the method that we use is necessarily incomplete. And then for interactive assumptions where the adversary additionally has oracle access, about this I'm going to talk in a later slide. Okay, just to give an example of the corresponding input and output to the tool. So here we have just a simple example, DDH in the type 2 group. Then the tool input, so you specify the isomorphisms, the maps, the common adversary input, and the left-right adversary input. And then you run the tool, and the tool either returns that it's valid, or in this case, it gives you the attack where the adversary takes x, uses the isomorphism to send it to G1, and then multiplies x and y, and then compares the result with this. And then the check succeeds on one side, and it fails on the other side. So now for parametric assumptions, so here the main difference is that the adversary input is not fixed. So to express this, we have to allow for range expressions. So here we say for all I in this range, and here we have range variables which are also undefined, so we want to prove it for all n. We give out x to the power of I. So we have these two range expressions, and we see that there's just, we use these to express the gap that is here between x to the power of n minus 1 and n plus 1. And then this is a challenge. And then this is translated to a set of constraints over the integer, and then the SMT solver finds out that there is no solution, so this is contradictory, so there cannot be an attack. Okay, now for interactive assumption, the main difference is that the adversary can actually choose values when he queries an oracle or for the winning condition. So what we do is we introduce parameters for these values in Z, choose them as the adversary, and then we translate the assumption into a logical formula that contains polynomials over these parameters. So we have a conjunction of polynomials that must be equal to 0, and a conjunction of disjunctions of polynomials that must be not equal to 0. So so the equalities usually come from let's say, from the verification equation of the winning condition, and the inequalities come from additional constraints. If you have an interactive problem where the adversary should produce a signature on a new message and not an existing one, so you get an inequality from this. So for the bounded case, we use computer algebra systems to perform Krupner basis computations to check if the formula is contradictory. And if we cannot prove that it's contradictory, then we try to find an attack using an SMT solver. And for the unbounded case, we cannot directly get this finite set of polynomial equalities and inequalities, so we have to compute a symbolic approximation of this and then use SMT solvers to find a contradiction. So here's, for example, the input for the mLRSW assumption. So we have the oracle definition, and we have the winning condition here, and we have equalities and inequalities. And we can also talk about the oracle arguments here. So this is implicitly all quantified for all queries here. So if we take, for example, the modified mLRSW assumption was proposed in CCS 2007, and then later on an attack was published, the tool can prove that it's secure for one query, but as soon as you allow for the second query, it finds an attack and gives you out the right oracle queries and the right values for the winning condition. Okay, so now to conclude, we have developed a method for the automated analysis of assumptions in the generic group model. Then we have implemented this. And here are some results just to give you an overview about the different types of assumptions that we cover. And maybe we should give a disclaimer here that it's your own responsibility to use the tool, so we don't encourage you to come up with many new assumptions. Okay, so there are several venues for future work. So the first one, which we're currently following, is to integrate the analysis algorithms into a tool chain for synthesis of schemes. And we're looking currently at structure preserving signatures. And another direction is to see if the methods are applicable for finding reductions between assumptions. So if you have two computational assumptions, you can directly take the tool in the interactive mode and then find an attack which corresponds to an assumption. But for the decisional case, it's much harder. Okay, thank you.